All right. Hi, everyone. Well, this is our working session for a physics project. And actually, the big theme here is understanding multi-way systems better. And I got interested in kind of what you might call an analogy with multi-way systems with games, because a game, the different possible moves of a game are like different possible moves in a multi-way system. So this, for example, someplace here is tic-tac-toe. This is a very simplified form of tic-tac-toe, one-player tic-tac-toe, where at every step you can make multiple different moves. Now, I think one of the things I wanted to do, so I've looked at part of the goal here is to use what we understand about games to understand things about the topology of multi-way systems and also about coordinatization of what amounts to branch Hill space. So in a sense, the analogies probably are that the scoring of the game, the winning of a game is like a measurement in quantum mechanics, where you've basically taken multiple microscopic configurations and you're projecting all of them onto this one player one state, for example. It's also so among the things that I want to look at are causal invariance for games. Ed, maybe you have a comment on the role of let's see. I mean, when there is causal invariance, it means that as you go through the game structure, if you ever, you can always recover. Whatever direction you go, you can always recover. I mean,
so one thing would be capturing a piece in chess.
Well, okay. So hold on. So you're okay. So first of all, we've got potentially we have final winning is presumably like measurements in QM. Now, I don't completely understand what, I mean, I have a feeling that there's one first point, which is even the notion, let's see, the notion of winning is like putting in, it's kind of like putting in foliations, I think, in these graphs. Jonathan, this would be a good time for you to pay attention to this, because this is where.
Let's not do winning first. Let's do possible moves first, and there would be what pieces exist, moving pieces, deleting pieces, adding pieces.
Yeah, but is Jonathan with us or not?
Yep, yeah, I'm here.
Okay. So what I'm trying to understand is there are cases of games like tic-tac-toe where there's no, so that's a tic-tac-toe, that's a complete kind of game graph for tic-tac-toe, right? Where these final nodes here correspond to different winning states, different states being the winner, so to speak. But you can also have kind of a tic-tac-toe that has no winner, where you're just, I don't think this is it either, maybe this is it, where you're just, that's still checking for wins, but where you just keep going until the whole board is filled in. You don't worry about terminating time when somebody won, if that makes sense. Do you understand what I'm talking about?
Mm-hmm.
Yeah.
Okay, so I think the analogy is that the quantum observation frame business is analogous to saying, I think, there is this, in this structure that you're building, in this multi-way graph that you're building, you are somehow putting in this quantum observation frame that corresponds to, that somehow corresponds to a measurement, in the sense that it is saying, given this set of, this set of things, you will freeze time and consider the game over. Did that make any sense? No? Jonathan, did that make sense to you?
I think I pointed that out yesterday.
Which?
That the measurement, the outcome of a projective measurement and the outcome of a game are both, essentially singularities in branch yield space. They both correspond to situations in which your reference frame is forced to freeze time around a particular state.
Yeah, I think so. Right. So, okay. So then the next thing which of interest is, if we look at the branch yield graph, and I'm not sure it is completely the branch yield graph, but if we look at we have this notion in this picture, I think, of moves in the game, right? So moves in the game correspond roughly to time steps. Is that right? Roughly roughly to time steps in some cosmological rest frame. Does that make sense? Am I?
Yes.
You understand what I mean by that, Jonathan? Do you?
Right. It's worth making a point between turn-based games and real-time games.
Okay. What is the distinction there?
In real-time games, there's no time step.
What's an example of a real-time game?
Fighter game.
What?
Computer fighter game.
I know, but okay. We're not talking about continuous time games.
Mm-hmm.
What games are there? I mean, obviously in a solitaire game, there's no turn-based notion.
Correct. One card game that's real-time is called Twitch.
Have you ever played a board game called Diplomacy?
A long time ago. I'm not a big game player, unfortunately. I mean,
Okay.
like 50 years ago, I think I might have played that. Why?
Because Diplomacy has this very interesting mechanic where the turns actually all occur simultaneously, right? So what's happening is you basically have to resolve branch pair conflicts in real time, because what happens, how it works is, it's a military strategy game where everyone writes down that, that you say, fleet goes to, fleet Sevastopol goes to Trieste or whatever. Everyone writes down the moves they want to make in the upcoming turn. And then each person sequentially reads out their moves. But then if there's a possible conflict with something else that someone wants to do, then that has to get resolved kind of offline. So the idea is the dynamic works by everyone's moving simultaneously, which is quite different to how most of these strategy games work. And it means you have to deal with, essentially branch pair resolution.
I see. Are there other games, Ed? Do you know if there are other games that work like that?
Yes, quite a few.
Like what?
There's a number of items in chess variants that work like that, where players write down their moves, their desired moves, and then a referee figures them out simultaneously in various resolutions for that. Pretty much any game can be turned into that sort of mechanic.
Okay, so then how do they resolve the branch pairs?
Diplomacy has a very elaborate set of rules for doing that. Others, sometimes the turn will be skipped if there's a conflict.
I see. So, okay.
For example, there's blind chess, where you don't know whether or not a move is legal or not. And neither person can see the full board. They just see their own pieces.
Okay. All right. So in other words, rules for resolving conflict, or skip the turn if there's a conflict.
Mm-hmm.
And in Diplomacy, it's kind of interesting that there's Sorry, I'm going to nerd out a bit here because Diplomacy is one of my favorite games. But there's this interesting mechanic where effectively what you're doing is like looking at common ancestry in a multi-way system. Because if you're, suppose you come up with some elaborate turn that basically has a lot of causal dependency between events where you're going to move this piece here and then move this other piece there, but that can only happen if the first piece moved. And then there's a conflict with the first piece. You essentially have to traverse, kind of back up the multi-way system, change what needs to be changed, and then kind of traverse back down again.
And some really good players at it will try to set up those sorts of conflicts so that they can pull off something spectacular because a whole bunch of people didn't expect interference.
Exactly, yes. It's like you tweak one event in the causal network, but suddenly loads of other things have to change. That it's quite hard to foresee.
It's interesting.
For example, I remember one game where I tricked France into backstabbing Germany and also backstabbing me, but the France-Germany conflict caused everything they were doing to fall apart, and I managed to get the only movement that was worthwhile.
Okay, part of the overall objective of this exercise of the correspondence between games and quantum mechanics is to get more intuition about quantum mechanics, to make more familiar some of the things that happen in multi-way systems. So that's kind of interesting. There's a notion of backtracking, backtracking the branch pairs. Okay, so this, by the way, from Nick is apparently a better tic-tac-toe, which I'm not surprised by. Oh, proper alternating tic-tac-toe. Did I get it wrong? Shocking.
Well, yes, yours wasn't alternating.
No, we made it alternating by having explicit step numbers in the states, but you can do it without the needs for step numbers.
How can you do it without the need for step numbers? How does this work? Well, we can try running this in just a second. But we still have to check for wins, don't we? In any case, so let's keep going here. So okay. So I guess I'm asking, as you go across the game graph, how do you identify? Is it the case that there are games where you're not just using flat foliations to determine, in other words, where depending where you are on the game graph, the time runs at a different rate?
Well, arguably, sort of skip a turn, miss a turn dynamics in board things are like local slowdowns.
Miss a turn is the analog of a foliation that isn't flat. Is there anything else like that? That is okay. So in other words, what you're saying is, if depending on, but that's a state dependent thing. That's not something that comes from outside the system.
Right. Usually.
Right. So I guess I'm asking, other than winning, is there any other action that causes one to kind of modify time in these games? And winning is a like a singularity, like time stops when you win. When somebody wins. Okay, so let's keep going then. So the next question is scoring in the game, or the next question is basically.
Well, there's usually two things. There's scoring and there's instant win and scoring. For example, with some in a row games, the winner is the person who got the most lines that have 4 pieces in a row or something.
Okay. So how to determine a win? Either scoring or instant winning. Is that right?
Mm-hmm.
Okay, but another question is, if you are going to evaluating a position, an intermediate position, is that a thing that's a thing that makes sense to do in many of these games, right?
Right. For example, in Go, who has the most territory?
Right. Or in chess. Are there, I mean, so when you evaluate an intermediate position, okay, I'm going to ask two questions. First of all, one thing you're doing is giving a valuation to that position. That's one possible thing you might do. Another question might be, what positions are nearby? Right. So when you evaluate a position, is that not, I mean, like in chess, isn't there a way of just assigning a number to a position?
Yes. And that's usually done.
So is that done more trivially in tic-tac-toe and things like that?
Yes.
What is the number you assign to a position in tic-tac-toe?
A number of threats you can build up.
Okay. So
it might be better to use Gomaku, the 5 in a row game, or Pente.
Ed, you know all these games. I know none of these games.
Just call it 5 in a row.
Which is that tic-tac-toe with 5?
Yes. Mm-hmm.
Okay. All right. Okay. So then what you're saying is that there's a way to assign a number. So in this graph, I could be putting a number at every node here. Is that correct?
Right. And basically the threats in that game are somebody has 4 in a row. That means they could win on the next turn. And lines of 3 in a row that aren't blocked are potential 4 in a row threats.
In each thing here, in this tic-tac-toe thing, I would be basically giving a number for each player, right?
Mm-hmm.
For each player, for each configuration, right?
Mm-hmm.
So that's like a very simple coordinatization of this thing.
Right. So in tic-tac-toe, a win one step back is 2 in a row threats.
Okay. But so this is like an energy function or something. In other words, this valuation function for any given player progressively increases, and when it hits some value, they've won. Is that correct?
Right.
Okay.
When they have in that game, when they have a sufficient number of threats.
Okay. All right. So then there's a question of what positions are nearby, and when does one think about that?
Well, I think that's kind of related. I mean, so my understanding is that, okay, one of the simplest ways you can evaluate a chess position is to use what's called leaf evaluation, where you just you look ahead a few plies, you look at all possible positions, and then you just see what happens in the leaves of that tree, and then you score the leaves based on what material gets captured, and then you use the total score to determine to evaluate the original score of the position you started.
Okay, so your point is that the common light cones there of other moves. Okay, so then you're saying look ahead, scoring by look ahead.
Right. So I think one of the simplest chess evaluation functions just says go look ahead. I think it's like 4 plies, and then and then just look at what material gets captured, and then you weight things a little bit based on central pieces are worth more than pieces outside and so on. But basically that's the idea. You look at what material gets captured on each leaf of that tree, and sum that to get the position, to evaluate the score of the position.
So by the way, what do we call light cones in multiway systems other than entanglement cones, which is very quantum mechanical? We probably should have a notion of branch cones, which is the set of states. We don't have a name for that, do we, Jonathan? It's a set of states that
you call them entanglement cones.
What's that?
I've just been calling them entanglement cones.
Yeah, I know we've been calling them entanglement cones, but that's very quantum, that's very quantum oriented.
Well, light cones is very relativity oriented.
Well, fair enough. All right, whatever, branch cones, entanglement cones, whatever. So those are the game states you can reach. The forward entanglement cone is the game state, the forward entanglement cone is the game states you can reach from your state. So, for example, an event horizon in the game corresponds to, those are then states you can never, that defines a class, that breaks the state space up into states you can never reach. Makes sense? Is that right?
Mm-hmm.
Okay, my next question, let's talk about superposition for a second. What is the analog of superposition is there an analog of superposition in games? For example, if one player doesn't know what the state of another player is or something, is there some analog of superposition? Superposition basically just means that you've got a whole bunch of different states and you're going to treat them all together. Am I being confused, or?
I think blind chess would be an example.
Okay. So blind chess is, what are you doing? You're just saying,
you've got just your pieces on the board and you don't know where any of your opponent's pieces are, but you can assume that they started in their starting positions. But you don't know what your opponent has moved until you pick up clues based on when the referee tells you you've captured something.
Or you can't move there.
Right. Mm-hmm. So typically the start of a blind chess move is to try all the pawn captures. The referee will say whether it's a legal move or not. And if you don't capture anything, then you try other moves. And that lets you get a map of where the opponent's pieces might be. So even though you've only taken one move, you've tried 50 moves.
Yes, I understand. But, well, that's maybe a little different, but what about, I don't know how to play any of these games. What about these card games where you don't know your opponent's, cards and things?
Right, poker or bridge.
Right.
That's more of an odds game.
No, but that's the point. That's quantum mechanics, right? Because that's the thing is that you don't know. It's like the famous quotes from Einstein about playing dice and so on. This is, in a sense, again, I don't know these games really, but these games, the opponent has a bunch of cards. You don't know the state of those cards, so you don't know. So you're in some region of this graph, but you don't know exactly. You know a little bit of information about what region of the graph, but you don't know the whole story.
And Mao would be an example of a game in which there's a rulal superposition.
I don't know these games. You guys are so ahead of me. I don't know what is it.
Okay,
Mao spelled like that?
It can be spelled with an O or a U. It's I think it's transliterated both ways.
Okay. What is the game?
So the idea is, okay, so one player essentially picks a set of rules for it's a card game. So one player invents the rules and they don't tell anyone. And the rules essentially say under what conditions you're allowed to discard certain cards. And then what happens is that the players go round and attempt to, the goal is to try to get rid of all of your cards. But if you play in a way that's inconsistent with the rules, then the player who invented the rules will tell you that you've done something that's inconsistent and you have to take up everything that's been discarded. And so usually the first person who reverse engineers what the rules are ends up winning. So that's an example of a situation where you have both branchial and rulal superposition, because at the start only one player actually knows what the rules are.
Right.
A classic game that changes rules is called Flux, Flux.
Okay, but I want to come back to the more traditional kind of superposition, where you don't know, where there are many possible paths that you could be on in this multi-way graph. You know your own cards, you don't know your opponent's cards. And what is the analog? I'm trying to understand the analog of measurement and so on. And then we're going to think about the bizarre question of the analog. I mean, so the odds are basically the path weights here. The odds of different things happening are the path weights, presumably.
Right. One game you could think of is Stratego. If you're familiar with that one.
I've heard of it, but
you know where the pieces are, but you don't know what the values are.
Okay. Well, okay, but let's try to understand the analogy here. So the odds in the game, in any game, that where you have certain missing information, or even where it's a game of chance, the odds in the game are the path weights in the multiway graph. Am I right, Jonathan? I mean,
yes. Or I mean, they're determined by the path weights. Yeah.
Right, but the odds of being at a particular configuration, okay, so you may have a conditional probability because you may know you're in this region of the multiway graph.
Exactly. There are very few games, I'm not aware of any, where you start from literally zero information, right? You usually
right. So then you build up conditional probabilities. So that's kind of interesting because it's like doing partial measurements, partial traces, so to speak. Build up conditional probabilities by knowing what region of the multiway graph you're in.
I'd say Go might count as that.
Okay, but then, okay, so my next question is, the position in the multiway graph, which is our famous branch shield coordinatization, is this question about, laying out all the configurations of the game in some kind of meaningful coordinatized setup, right? So let's take tic-tac-toe as an example. Maybe you can give me another game. But in tic-tac-toe, if I were going to coordinatize all the board configurations, what would it look like? What would I do? Is there a natural way to do that? So I'm saying, so I mean, in other words, I've got all these different board configurations, and I'm asking the question, can I assign, I mean, you've said there's one coordinatization, which is this incomplete, with this one that's based on the threat number and things, right? That's a coordinatization, which tells you with respect to threats, see, I think it's very closely analogous. Jonathan, I mean, this whole business about doing completions, we're going to ask what completions are here in a moment. You get what I'm saying? That we're trying to figure out what is a natural coordinatization here. If we were going to, say what's close to what in this coordinatization, how would we do that? How would we evaluate? We're trying to evaluate configurations and decide their closeness to other ones. Does that make sense?
Mm-hmm. It's worthwhile to mention another game where everything is predetermined and you're just basically going through the motions. There's basically never a choice. One example is Candyland.
Okay. I mean, it sounds like a boring game if there's no choice. So is it the case that the game graph is a single there's a single line in the game graph? Is that true?
Yes.
Okay. But okay, that doesn't sound very exciting. But now, okay, so let's talk about completions. Jonathan, are you with us here?
Yeah.
Okay. What is a completion in a game?
Well,
it's saying, go ahead.
It's the same as a completion in any multi-way system, right? It's saying that because you end up in this winning configuration or this losing configuration or whatever other measurement outcome there is, it didn't matter whether you went this way or that way, you still end up in the same place. So you're defining an equivalence relation between states.
Right. But the question is, what is the natural equivalence relation? So you might say, what would be some natural equivalence relations in games? That is, places where you don't care about the difference between one configuration and another.
Well, in games like drafts that have a high degree of symmetry, you're opening
checkers for American audience.
Oh yeah, sorry, checkers. Yes. So one day I will complete.
It's okay. I don't know most of these translations. Go ahead.
But yes, no, sorry. So in a game like checkers where you have a very high level of symmetry in the board, your opening is equivalent up to a Z2 transformation, right? It doesn't. It
yes.
won't. I mean, I guess the same is true in tic-tac-toe. I mean, the initial move in tic-tac-toe is equivalent up to actually it's more than a Z2. It's a Z4 or something in the tic-tac-toe case.
Tic-tac-toe / checkers.
So I mean that's a trivial equivalence relation, but then the point is that the completion gives you a way of computing all equivalence relations that preserve the outcome, right? So it's you're basically saying, I know that I'm going to lose. What are at every point I make a decision, there are several other decisions I could have made that are also going to yield a losing outcome, and I'm just asking, what are all of those equivalent decisions?
Okay, but let's walk through a little bit more carefully the analogy with quantum measurement. Okay, so we have, so normally we can draw out the tic-tac-toe thing without winning and losing. Okay, and maybe we should do that. We should just draw out. Let me just do that. We can use Nick's tic-tac-toe function. Let's see. I need to make the multiway graph. I need to use my check. Oh, I'm going to do it without the check win function, right? So here's my check win function. And I need the plot board function. And we will use Nick's superior tic-tac function. Okay, so this is now going to be, let's just do it for one step. All right, so this claims to be, let me remove, okay, this is with, okay, this is the, what is this? Is this a 2-player? This looks like a 1-player. Where is the thing that determines whether it's 1 or 2-player? Isn't that thing, oh no, it's 1 player because there's only 1 move, right? I get it. That's the first move. Now, if we do 2 moves, we'll see the first player and the second player. Beautiful. Makes sense? Everybody agree on what this looks like?
Uh-huh.
Okay, let's just do the third move for a second. Wow, surprisingly unsymmetrical. Does that surprise you?
The layout is asymmetrical.
Well, yes.
Not really.
Okay. All right. So now let's do this. Okay. So at some point here, if we go like 6 steps or something, well, even 5 steps, we will have, this will go to 2. Was my code wrong? I wonder from previous, okay, let's go down to size 20 here. Okay. So this is now showing, claims to be the correct alternating tic-tac-toe. I wonder if my previous code was simply incorrect for this. Okay, so this is alternating tic-tac-toe with winning, right? Now let's consider alternating tic-tac-toe without winning. Okay, so that's just apply this tic-tac function. I think we can just do this. Am I wrong? Okay, so this claims to be, I'm just really surprised it isn't more symmetrical, but maybe that's because it breaks symmetry with that first move. Okay, so this claims to be the full tic-tac-toe object,
I'm also wondering why you expect the layout to be symmetrical. It's not symmetrical in, other similar cases. Why would tic-tac-toe be special?
Why? Just because it has its symmetry of the square.
Yeah, but I mean, strings have symmetry of the string, and their state graphs are not symmetrical.
All right. Well, okay. All right. So let's look at this thing. Okay. So what I want to do is compare this, which is the this is the thing with kind of a with a notion of winning, right? And this is the thing without a notion of winning. So my question is, explain to what extent this is like quantum measurement. What happened there? Jonathan, do you have a good way to describe this? I mean, we're doing a projection here that projects onto this state or this outcome or this outcome.
Right. And so you could then define a set of completions that preserves, the measurement outcome, but collapses all the other branches together, under some equivalence relation. And then you're just saying, okay, then given that we know that, player A wins and player B loses or whatever, here are purely classical trajectories we could have taken where we didn't require any decisions.
Right. Let's walk through that, though. This is a nice analogy. This is actually working out quite well. This is going to be useful. Okay, let's walk through it more carefully. So what we're saying here is this is no measurement occurred in this case. We're still in a superposition state here. In this case, we chose to make a measurement by deciding that something was winning or losing. And I'm just trying to understand. I mean, if we do this with quantum observation frames, for example, okay, we can do this with foliations, we can do this with completions. Is that a true statement?
Yeah, right.
We can freeze this with a foliation in which basically all of these states, what does the foliation look like? The foliation under here, so we're going down chunk, one flat foliations, right?
Right. And then, I mean, the minimal case would be on the last step, the foliation increases by a time step of 1 on the left, but doesn't increase on the right. So you end up with just one state on the last.
What do you mean? What do you mean? I'm sorry, I didn't understand. In this case, I mean, maybe we could actually draw the foliation. How about you can annotate? Why don't you annotate the screen here, Jonathan, if you want to, and actually draw this?
How do I do that?
You go to the tools at the top and you select the thing that says annotate, which has a icon of a pen.
There are tools at the top. Wait, do I have to be sharing screen to do that?
No. Get whatever it is, whatever mouse down, whatever hover thing you need to go to the side of the screen or whatever, bottom and top of the screen. It should bring up a something that allows you to annotate.
Gosh, I can't seem to get this to work.
Anybody else know how to do this?
Yeah, Jonathan, I'll send you a screenshot of how to do it.
Okay, thank you. Sorry about that.
Okay, in any case, we could also use your code. Where is that foliations code?
You had it in the Euclid post, right? Oh, speaking of which, I got the foliations working for Euclid, I think.
Oh, thank you. Thank you very much.
They're a bit ugly looking because the graph is a bit ugly looking, but
don't you have a foliations? Didn't you have a precursor of a function repository entry?
Yes, which I think you called.
Oh yeah, there we go.
Foliations or something.
Post set foliation graphics.
Yeah.
Okay. we need to clean this up. But okay, so then what this is doing is, this is a states graph, and then you give it the things that are at a particular step, right?
Mhm.
So in this case, what will we be giving it? We will be giving it the configurations. Oh, look at that. He is
Okay,
flying.
yes. Is it working? Excellent.
Yes.
Thank you. Okay, so we have, if we had foliations that looked, oh, sorry, that's not meant to be curved, but if we had sort of the standard flat foliation thing, right?
Yep.
And then at the final step, okay, we're going to break hyperbolicity a little bit, but that's okay. Then you just evolved on the left, but you didn't evolve on the right.
Well, but wait a minute. That picture isn't right, because evolving on the left continues down. I'm now very confused. I mean, actually, in this particular thing, no, but you see, evolving on the left, you actually would be adding a purple. I see. The point is you already won, and so the fact you add a purple is irrelevant.
Right. So once you've reached this state, then that then you're in the singularity state, and then nothing else matters.
But you're saying that then on this side, you're saying we continue the evolution on this side. It's not going into that one thing there. It's continuing all the way down here. These are being continued, but this froze over here.
Right. Exactly. Yes.
Fair enough.
Yeah, like in those quantum measurement string pictures that you have in the.
Right. But so this is one interpretation: is we made a measurement in which we chose to freeze whenever we already, once we had won, we froze. Right.
Right.
Okay. Now the alternative picture is a completions picture,
mm-hmm.
in which we basically are making a single equivalence class of the things that have that winning outcome there.
Exactly. So, just like with a theorem prover, when you've introduced all the critical lemmas in the theorem prover, it's trivial to prove whatever theorem you want. You can just do it mindlessly by applying all possible rules. In the same way, once you've introduced this equivalence class in your game, winning or losing the game requires no thought, right? You just follow the rules.
Okay, let's do it for this game. Okay, here, why don't you erase your thank you. Okay, all right, let's do it. Let's actually create the completions for tic-tac-toe that make winning obvious. Okay, so here, by the way, what we would do here, by the way, is, I mean, in our foliation world, what we're saying in this case is, actually, what we want to do here, hold on, let me just compute this. So to make our foliations, what we would do, we compute this thing, that will give us those states, right? So the most obvious foliation story would be this thing here, and we would then say post set foliation graphics of just this, and that should give us flat foliations, if I'm not mistaken. Do you agree? Humph. Okay, let's try to understand what happened here. Oh, I see. It did give us flat foliations.
They are flat foliations. Yes.
Flatness is in the eye of the beholder. Right. Why does it double up every foliation here?
I don't know.
Okay.
That version of the code is needs some work.
Okay, but now let's consider the case where anything which is already won which means we're running check win on these things, right? And anything which is already won, time has frozen for it, Does that make sense?
Right.
Okay, so we want to say select this thing. Actually, it's at level 2. Well, it depends on whether we want both possible wins, a win on either side to freeze time, or only a win on one side to freeze time. I think we want a win on either side to freeze time, if I'm not mistaken. See what I'm saying?
Yep.
So we're going to need a slightly different case to see this, to make it more interesting. I mean, Ed, is there a the 3x3 case is going to get quite complicated. Well, then maybe, I mean, it has 5,000 states, the 3x3 case. Okay, so let's do the following thing. So let's say map check win onto this at level 2, and we should see. Oh, for goodness sake, what the heck does that mean? Why does check win say that? How is check win defined? Check win of a list. That's weird. What is this saying here? Okay, hold on. Map, did I get this wrong? Map at level 2, right? So this thing here has, if I say, for example, in this map framed at level 2, those look like they're board configurations. Oh, silly. It's because of those null lists at the end. All right. Okay. So now let's say map check win. What? What's going on here? Do you understand, Ed? Do you see what's going on here?
I'm looking at it, yes.
Let's just check win. What the heck is going on? Because there should be winning configurations here, right? Oh, it may not like it when there's two winning, when it wins in two different ways. But still, this. Oh, Jonathan, you're crazy two expression thing.
I didn't tell you to use multi-way function system for this.
What do you think we should use?
Multi-way system with a state evolution function. Multi-way function system, as the documentation says, is really intended only for functions over the integers. Anything else is undocumented behavior and therefore not my problem.
Right, okay. I think I had a version of this which used.
Yeah. The versions we were looking at yesterday used multi-way system with a state evolution function.
Oh, that was for something different. That was not for tic-tac-toe, I think.
Really?
Well, let me look. Let me see what I have here. Oh, this does have. I'm sorry, it does have that.
Right. And this should work because, yeah, this is what it's intended to do. Multi-way function system is not intended to run functions that are not over the integers.
Okay, but this now had, by the way, this, Ed, do you believe this? This claims to be the game graph for tic-tac-toe, including the very bizarre little thing down there.
Not really, because there's only one final state, but there's like multiple end states for tic-tac-toe.
What are you talking about? Look at all these final states.
Oh, I see. Okay.
Except there's a singular one here, which is very weird.
Yeah, that looks weird. There's multiple end states where all the cells are filled.
All right. Well, anyway, we'll get to this. Okay. So let's write this more carefully. Okay. Okay. So let's say, all right. So let's say this is, so that's Nick's tic-tac function. So we keep track of what's what here. Okay, so now let's say we say here, okay, so now we're going to say tic-tac multiway, tic-tac MW, and now we're going to have the initial condition, the number of steps, and options, but we also need to know this is a bad way to do it. You're saying, I mean, so this thing here has the alternation is built into Nick's thing. How does the alternation work in Nick's thing here? Oh, it simply counts how many of the previous things.
Right, exactly. You can work out what the turn is by just looking at how many things are laid on the board.
Right. Okay. So I mean, we might want a non-alternating version of that as well. But here, did we have a version here? Yes, this one here doesn't have. We are going to want an event function as well, but let's see. Okay, so the tic-tac association is basically this thing here. State equivalence function, blah, blah, blah. Oh God, we've also got the state rendering function. I'm just thinking how to package this thing, because we got several different. Oh, let's just put this association in here and not worry about the other stuff for a minute. Okay, so that's our association with winning. Tic-tac win association, and then tic-tac without win association does not have any of that stuff and just says, oh God, we need to know, you know what, we need to clear that. This should be a function of k, the number of players. And that's there. Okay, tic-tac association of k is, so I think the state evolution function is just tic-tac function of k, if I'm not mistaken. Right? Do you believe that? Okay, so then here, this becomes multiway system. This becomes, this whole thing here becomes tic-tac association of 2. Okay, that's encouraging. Okay, so then here, this thing is just the 2-step version of that. And And then this is the 3-step version of that. Okay, magnificent. So we might want to make that slightly smaller there. Okay, so now here, this is we can just use a 4-step version, right? That's enough because there's only 4 things to be filled in. Okay, that's tic-tac association there. And then if we say tic-tac win association, that will include winning. Great. All good so far? Okay, so now we got these 2 things, but with layered digraph instead. Just trying to be mildly systematic so that we don't mess this up completely. Okay, there's the layered digraph version of that. And that's that one. Okay, now let's try and foliate these creatures. That was the exact same picture I just had. Okay, multi-way system of tic-tac association of 2, 4 steps. Okay. Okay, so now this is just this thing here. With post-set foliation graphics of that, this. All right, a slightly peculiar thing, but at least there are no errors and so on. Okay. Magnificent. Okay. Those are our wins and whatevers. Okay, so now what we want to do, it's actually rather boring in this case, right? Because in this case, we win after it's a fixed number of steps to the win, right? Right? So the foliation that we use for this case here will just be frozen. Jonathan, if I'm not mistaken, it just freezes at this step.
Well, yeah, obviously.
Right. So it isn't very interesting in this case. In the bigger case, the 3x3 case, it might be more interesting. Okay, so now if we wanted to do the 3x3 case, we would, okay, so in the case where we have winning, is there an intermediate case? Ed, is there an intermediate case? We have to go to 3x3.
There are some rules for 2x3, and you can always do mini go if you want something really complicated. Even 2x2 and 1x3 are complicated with mini go.
What do you do? Is it different winning criteria or what?
There's Japanese and Chinese winning criteria.
Okay,
and
just what are they?
Well, Go rules are slightly complicated. I won't be able to explain it and the difference in 10 seconds.
By the way, the Nick is saying it should be symmetrical, by the way. Somebody was asking about purple versus whatever. Okay, hold on. This is a better version of check win by Nick. Well, that's a good use of anti-diagonal there. All right, so this is Nick's check win. Is it better or is it just faster? Do we know if it's different or does it have different behavior, or is it I wonder whether it can do non-square boards. I was wondering if there was a better way than this whole nonsense here. That was very Neanderthal, my code. Well, okay, so let's try doing this. Okay, so we would be doing 9 steps here, and we will be saying 2 players, 9 steps, 3x3 board. Right? That's going to make that will make a big complicated mess. Let's do the win case first. Is there any way to speed this up? So this is basically creating the game graph for full tic-tac-toe. I don't know why it's quite so slow, actually. Should I be worried here? Anybody want to comment on this? Anybody? Ed, are you still with us? I mean, we should be getting a picture like this. Oh, there's a horrible mistake. Horrible mistake. Damn. This is going to crash. Damn. Okay, guys, come on, please pay attention. Why was that wrong? Exercise. Look, we were generating, this was a states graph. Ed, you're saying in these various rules, but we need code. I mean, in other words, you're saying you can. I mean, I can paste this in here, but I mean, we need. If you're saying that this is something that will work even on a tiny board, or this is only interesting on a larger board.
No, they're interesting on tiny boards, and it's well analyzed. There's some really good papers on the extreme trees that are.
Okay, Ed. What this means is this is simply a different foliation of this graph in the end, right?
Mm-hmm.
Okay, I'm going to generate this whole graph.
But if this was 2x2 go, there would also be prisoners that were captured. So there's basically scores on both sides in addition to the graphs.
What are you talking about? Look, what we need to know is, given a board configuration, who's the winner?
Mm-hmm. And it's more complicated than that in Go.
Okay, I know it is. Right? I'm asking a direct analogy of tic-tac-toe. You're saying there are alternative rules that aren't just the how many in a line type thing. Is that right? So on a 2x2 board, what do these rules imply?
That's probably too small, but
that's what I was saying. Yeah. So, 3x3.
Right. Well, there's also Frank Harari's snaky game, where you're not trying to get a line; you're basically trying to get some other shape.
Okay, but my question is, my question is this: each one of these possible games, right? Each possible thing, we could decide that any subset of these states, right, is a win for orange or purple, right?
Mm-hmm.
Right. So what you're saying is, I don't know why this is taking so long. How many states are there in this thing? Up to 9 steps. I mean, this one, I know there's 5,800. Actually, there might be a simpler thing we could look at. We could look at one player tic-tac-toe, right? Because one player will have wins at different stages, right? It's not the most exciting quantum measurement. There's only one possible outcome, but at least we'll have a thing at different stages, yes? All right, I think we have to kill this for now. Okay. Start again. And I want to move on to something slightly different, but okay, so let's take the one player example of this, which should be very straightforward. Unless you see any reason why that's a bad idea. Okay, this makes sense. So in the end, so that's the without wins, one player, yes? Does that make sense, guys? Are you still there, or?
Yeah, I'm watching.
Oops. Okay, so this is with winning. This is stop if you've already won. Okay, so in this case, so if we say vertex count 512, $451. Okay, now, how can we measure? I don't quite understand. Are these going to all terminate at the same point, or do they terminate earlier in some cases? Do you understand my question? Do you understand the question? Ed, do you understand the question?
I think so.
Okay. You don't know the answer, though.
I'm looking at that graph and wondering why it seems so symmetrical, but also skewed.
Which graph?
Oh, the
Which
upper
graph?
one there. That one there.
Look, this one here, right? Eventually, I don't know how we make the analogous picture. Okay, so just to remind ourselves what this picture is going to look like for the 2x2 case, right? There it is. Okay, that's the 2x2 analog of this.
Okay.
Right? I mean, sorry, yeah, that's the 2x2 analog. This is now.
No, I see. Okay.
Oops, I just messed this up by resetting this to that. Drat. Okay, so this cuts off 2 rows here, 2 time steps basically, because it has already won after that number of steps, right? But it wins at a uniform point.
Makes sense.
In the 3x3 case, does it always win at a uniform point? No, it does not. Right? It does not.
Mm-hmm. No.
It'll win at different points. Okay.
Yes.
So that means that the foliation that we could draw in this, and I don't know, is that foliation code efficient enough, Jonathan, that it could operate on an object like this?
Not the version that you're using.
Okay. Okay, but in principle, it would draw in here that the winning lines would be some kind of. Okay, so this is saying, actually, I don't even understand this layered digraph. So this is how many steps? This should be 9 steps altogether, right? Depth 9. How do I work out in a digraph what the okay, so there should be a longest path here. This thing here.
There'll be lots of longest paths.
Okay, but there's a path from here down to here, which should be 9 steps.
Right.
Correct? Right. So every particular game is a particular path through here. Right?
Yes.
Okay, but so this isn't down, this goes 9 steps, but there are other places where time gets frozen earlier if we had a win, if we had something that was a win. Now, can we understand by completions how that works in this case, Jonathan?
Right. The longest game without a win will be 6 steps.
You mean after 6 steps, something will always have terminated?
Right, but there is something.
Well, what's the shortest game? The shortest game that wins is 3 steps, right?
Right. Mm-hmm.
Winning games are won after between 3 and 6 steps.
No, 7. Correct? 7. There's a unique with rotation state with 6 pieces where there's no win.
Okay.
Basically fill in the board and then remove a diagonal. There's no lines of 3 in that.
Okay, this is actually telling us, for the 1-player case, this is actually telling us the number of distinct states, right? It goes up to 451 eventually, but that's the number of distinct states. So if I were to compute that for this case here, right, I can just stop there. And this is the number of distinct states. Okay, so there it goes. So there it is. That's the number of states. Right, there's your unique state that only resolve. No, that's the unique state where everything is filled in, right? Makes sense? Does that make sense, Ed?
Yeah, it does.
Okay. Okay, so what's this saying? This is saying that this is the number of distinct states where winning is one of the states. Is that right? Okay, you don't understand. Okay, never mind. Okay, so let's say for each case we want to say count in that the number of lists and count in that the number of integers. Okay, so this is saying the number of unresolved states, and that's just saying that the number of that we only count there as being one winning state. I think it's saying it's the slow speed is due to the layered digraph embedding. That is interesting. Okay, so this makes sense, Ed? This is giving you the number of unresolved states, right? Then that 6 is the number of unresolved states. And then you start getting winning states here, and then you've got the number of yeah, makes sense?
Yeah. Mm-hmm. I'm surprised that 6 isn't 2 though, because there's 2 states that are 6. You could do either diagonal.
Well, there must be more that are 6. There must be more that have the last, before you get to the state where everything has resolved. I mean, let's just find out what they are. Let's see. This is -3. What are those states? That doesn't look right.
Yeah, that doesn't look right to me either.
So wait a minute. This claims to be, this is supposed to be states that are stopped when they win, right?
Oh, okay. Yeah, that does make sense. Because basically, if you complete the diagonals in those, you'll see the unwinning state that was before. So that this is correct. There are 6 states at step 7 where there's a win, and that's the first time there's been a win.
What are you talking about? What are you talking about? These should never be generated. You're not supposed to ever see a state that has already won.
Right. The previous step, if you complete the diagonals in those, you'll see the 2 positions that had no wins.
Look, Ed, this is wrong. This code is wrong. You should not generate at this step. You should never generate something which shows a configuration which has already won.
Right. Basically, this code needs to stop 1 step earlier. This is showing the next step after the 2 positions that have 6 cells with no wins, and it's showing each of the ways a win can be made. And those are the 6.
This I know, but so this is incorrect. So what we need to do here is back over here, tic-tac win association. Okay, so this is saying the state evolution function. Oh gosh. Okay, this needs to basically map itself over tic-tac function. Right, and not return something which is a win state. Do you understand what I'm saying? Hey guys, please, could you pay attention so that
Yes, I am. I'm also trying to keep you from hearing a barking dog.
Okay. All right. So this is the function. Okay. So if integer q, we're already done. If it's just an integer there, we're already done with the state evolution function. If it's already 1, okay, so here what we want to say is if check win of hash not equal to false, with C equals check win of hash. If check win of hash, if C is not equal to false, then C else hash. Close for the width, close that, and this I claim. Okay, so this is now this is saying this is going to give a different result here, presumably. I called that win before. So do you understand what I just did? Okay.
That
yes.
makes sense.
Okay. So wait a minute. So this is now nice and symmetrical, which is good. It includes, I mean, basically what we might call post-win configurations, right?
You mean pre-win configurations, right?
No, I mean post-win configurations. This one includes configurations in which something has already won, like that.
Oh, I see. Right.
There.
Okay. I was looking at the one under it.
Okay, so then this one becomes much simpler.
Right.
Okay, so this is actually, I bet this is doable now. But okay, so then one player, that one is that. So now this is win before. Okay, interesting. Look at those things. Those are winning at different amounts after different amounts of time, right?
Mm-hmm. And getting down to 2 configurations before the last step.
Yeah, this looks much more correct. That's, so we want step -4.
There you go.
Great, those are correct. Okay, so here, rather boringly, it can only go one step. Oh, that's the 2x2. Yeah, that's the 2x2 case. Okay, all right. So just to recap here. So the sort of quantum version of this. Well, what is, Jonathan, are you with us still?
Yeah, sort of.
Can you pay attention just for a bit here, just while we try and go through this? I mean, okay, so the issue is this thing, we're comparing these two pictures, this picture here and this picture here. And they can be got, one can be got from the other by foliating this picture or by completing this picture, presumably. Right?
Mm-hmm.
So a completion would just be to say, let us combine, let us make a rule. How would this actually work? We should be able to add a rule that transforms. The completion is something that simply rearranges cells. What will the completion do in this case?
Give a winning position?
No. Jonathan, are you with us?
Yeah.
Okay, so the question is, what completion rule do we add to get the analog of this to turn into the analog of this? In other words, how are we adding rules that presumably are horizontal rules here, right?
Yeah.
That transform things so that we will get, so we turn this graph into this graph here.
Mm-hmm.
Do you
Right.
see how to do that?
Well, yeah, we perform a completion.
Okay, how?
The same way we always perform a completion.
Okay. Can we do it with multiway system? Can we do it with something inside multiway system?
Of course.
Okay, so why don't you tell us what to do? So
Ask for the completion.
what's that?
Ask for the completion.
Okay, so what do? We just literally say completion here?
Arithmetic's completion.
Okay, we don't want any of this stuff, right?
Yeah, it doesn't matter, but you don't need it. So after 9 steps, everything's resolved anyway.
Right, okay, so we want this to be after like 2 steps. Okay.
And then, yes, exactly as you say, basically all that's doing is it's not adding or remove, because these are horizontal. Each completion, obviously, as we already know, there's a one-to-one correspondence between completion rules and foliations. Each completion rule is acting only on the horizontal slices, so all it's doing is it's shifting ones around, but it's not introducing or deleting ones.
You know, Jonathan, you make it sound trivial, but this is actually fairly interesting, I think. I mean, it's really nice to have these concrete examples.
We could also do a factor 8 speed up by removing rotations reflections.
Well, we can write that code separately, but let's look at.
Do you want me to write that canonicalization?
Yes, but hold on one second. Let's just look at. Okay, so after 3 steps. Okay, so what we're going to see, Jonathan, this is more interesting than you are making it seem like. I think, at least, because what this then is going to do, right, is it's going to say we'll take one of these graphs. Now, okay, if we say after 1 step, does it have any useful completion after 1 step?
Yeah, it will do.
It should be able to. It should just map each one to. Okay, so then we take this and we apply inside here. Oh gosh, how do we insert these rules inside that tic-tac association? Is that going to be hard? I think what we want to do here, right, we want to say tic-tac association 1.
Oh gosh, yeah, I didn't think about that. Yeah.
Well, I think what we do is we just take that state evolution function and we say, we apply it to all possible functions, all possible things. Wait a minute. This evolution function will apply to everything, right? Oh, I see. So that, yeah. So all we want to do is the following. So we say tic-tac function of 1 applied to tuples of 0, 1. Does tuples let you do 2, 2? I can't remember. No. Okay, 4. Oops, and then we say partition that, comma 2. I never remember how this precedence works. You know what? I'm going to learn this once and for all. So in this case, I have to do this. Okay, so then what we want to say here is hash goes to tic-tac function 1 of hash. And then we probably want to do a catenate just for good measure. Actually, no, maybe we don't want to do a catenate. We do this, and then we say, oh, I need to do a thread, don't I? No, here I can just say catenate, I think. No, what happened here? Okay, help me out. So that should be a list of the possible tuples, of the possible configurations, right? Oh. Each one of those, yes. It's actually it's more like that. And then I think there's one level of catenation that's needed there. Okay, there we go. So that's the, okay, this is the this is the original rules. Okay, now we have that completion as those rules there. So we say append to this thing here. Oops, not append. Join to that thing there the completion rules. Okay, now I don't think we even need any of the fancy state evolution function, do we? We just can just do a straight evolution, can't we? Jonathan? Hello?
What is a straight evolution?
Well, I mean, we don't need to use the association, right? We're just going to give a set of rules there. Aren't we?
Oh, you want to use these hypergraphs? Okay, yes, you can do that.
No, I don't want to do them as hypergraphs. I'm doing them as, what am I doing here? I'm just, oh, you're saying I still need to use the state evolution function because it's doing something. It's just applying it to, we want to apply it. We're trying to apply it. Okay, this isn't going to give us the same, okay. You understand what I'm trying to do? I'm trying to do it with those completions, right?
Yes, right. And I was about to tell you a way to do that, and then you went and did something else.
Oh, okay. Well, tell me how to do it. I mean, if I just say replace, what the heck do I do here? I just say replace list of hash comma a rules. Is that right?
Pretty much. Except that you also want to have the state evolution function.
But this is the state evolution function, isn't it? Just replaces one of these states by a list of other states that apply.
Okay, fine.
Okay, now we need to interpret this creature. Okay, so this is with a completion. Okay, what do we conclude from this? What is going on here? This is showing those completions. What is going on here?
How do you get the states with only one cell on the second row?
On this row here.
Because after you applying a completion, as I keep saying, doesn't change the number of filled in cells. So
yeah, this is just, there's a path down here which is just following the completion rules. It's evolving, but just through the completion rules, not through the actual evolution of the tic-tac-toe game. See what I'm saying?
Okay.
But I don't understand, Jonathan. I don't understand what the analog is between. I'm now very confused about what the role of this completion is in being the same as freezing time with a foliation.
Okay.
Can you explain it in this picture?
Well, in this picture, no, because this is not a states graph, right? Well, I mean, it's a states graph, but it's
Okay,
one.
we can pick this one if you want.
Yeah.
So explain. Okay, so this claimed to have a completion which should have been equivalent. You're saying that the path from here, well, this particular case isn't very exciting because I'm confused about what the completion is supposed to do. So we've got these pictures. Assume we have two different winning configurations, for instance.
Right. Yeah. I mean, that's the minimal interesting case, and it doesn't work. It doesn't work any differently here to how it works in any other multiway system. Right. The completion rules map between states that are horizontally separated. Which states are horizontally separated depends on your foliation choice. So in other words, there is a one-to-one correspondence between foliation choices and completion rules, right?
Okay, let's just try something explicitly, okay? So what we're saying here.
Okay, never mind.
What? No, I didn't understand that. I didn't understand. I mean, okay. I was going to try a case where we could actually see what was happening. This would be the one-step completion here. Two players, one-step completion. What? Why weren't there more?
The number of states is the same.
Oh, right. Okay. Okay. All right. So then what we want to do is make this picture is this more illuminating? Is it going to be more illuminating if I do this one? Okay. Can you try explaining?
Which part?
The part that I cut you off from explaining because I thought I wasn't going to understand it. The part, how do I understand the correspondence between doing completion and foliating the thing around its win, so to speak?
Right. Well, as I say, just because this is a game graph doesn't mean it works any differently to any other multiway system, right? So you have exactly the same constructions you normally do. That when you say Knuth-Bendix completion, you're sending states to other states that are on the same horizontal slice, right? After say one time step.
Mm-hmm.
Above. But which states are on that horizontal slice depends on how you're coordinatizing the space. Depends on your choice of universal time function.
Yep.
So what your completion rules are depends on the choice of foliation, or as I keep saying, there is a one-to-one correspondence between foliation choices and completion rules.
I agree.
Okay, so then when you construct a foliation like the one that I drew on screen, where you are just sealing off a single state, what you're saying is all of the completion rules for all the states on that hypersurface get sent, all the states on that hypersurface get sent to one state, which is the winning state for one of the players. Right?
No, that part I haven't understood. So how do we construct how do we construct a completion? I'm confused again. How do we construct a completion that what was the last thing you said that takes? Okay, well, let's look here.
Scroll down. Yeah, scroll down again. Okay, so I can draw the same thing on screen that I drew earlier, right? So you construct something sorry, you construct something like this, right? That's your default foliation. That's the foliation that's implicitly used by Knuth-Bendix completion in multi-way system, right? So it's saying these states are equivalent, these two states are equivalent, these two states are equivalent, and so on. Okay, now at the final step, you pick a foliation that looks like that. So now what you're saying, now your completion rules are saying this state maps to this state maps to this state, this state maps to this state, and so on, right?
I can't see the this is if you have it. The annotation tool isn't showing your mouse position.
Oh, sorry. Yeah, okay. So I can say, so it's saying this state maps to this state, but it's also saying this state maps to this state, and this state maps to this state, and so on. They're all mapping to.
Is that right? Why are they all mapping to that state?
Because all states on the same hypersurface map to each other. That's what a completion rule does. Right. And crucially, none of them map to this state because that's not on the hypersurface.
Okay, so we actually should write different completion rules. But normally completion rules map between states on the same hypersurface, but we're imagining that that winning state is on a subsequent hypersurface.
No.
Which hypersurface is that? Look, the winning state is one time step beyond the explicit states drawn, right? So that foliation is still correct, right?
Yes, but then when we construct this one, all of these states are still on that hypersurface, except we've now added this new one, right?
They're on the previous hypersurface.
And on the future one, because we've violated strong hyperbolicity, as I said earlier.
But how do you achieve that with a, so what you're saying is, you're saying you add a completion where everything just goes to the winning state on the left. Is that correct?
Yeah, amongst everything else.
What do you mean amongst everything else? Amongst what else does it do?
Well, it does everything else that a completion would normally do, right?
Which is what? To map, I mean, given that you tell it, make a completion that equivalentizes a certain set of states. That's what the completion is going to do.
Exactly. So all of these states are equivalent, and they're also all equivalent to this.
I don't know what the this and this is. I think there's a way to make a mouse cursor.
All of these states are equivalent to each other, and they're equivalent to this state. But they're not equivalent to this state, just like for any other completion or any other hypersurface.
Okay, but the thing that's unusual, which is what you are talking about violating hyperbolicity, is the fact that you're saying that the states on that previous, that some of those states are equivalent, some of them are equivalent to something which is time-like, in the time-like future, in the future light cone of those states.
Well, yeah, because, as in ordinary relativity, right? Space-like singularities violate strong hyperbolicity.
Right. So the concept is, okay, so to freeze time to define a win, we want a completion that maps all states to that frozen time state. Okay. Now, why does it make any difference that we have completions that go between these states? If all that's going to happen is everything's going to just map to this guy, why do we even need, why does it matter that we have things that map between these states?
I mean, ultimately, it doesn't matter, just as in the singularity case, right?
But so what does it even mean that we are adding those earlier completions?
So if you're heading towards a space-like singularity, it's inevitably in your future, but until you reach it, there's other stuff you can do, right?
All right, fine. So you can, okay. Okay, but now in the case that we're seeing here, this seems like it's a quantum measurement with two outcomes. so how can we see that? I mean, I mean, we could create these foliations for either of these outcomes, right? But I'm just trying to understand, in terms of the formalism of quantum mechanics, how do we think about this? And in particular, the thing I was hoping to get to was, how can we think about phases for these different things? So we've got path weights that gives us the probabilities in the game. How do we understand conditional probabilities in the game, and how do we understand phases? What do phases mean in the context of the game?
I'd say those would be turns.
No, I don't think so. The phase, look, Jonathan knows what I'm talking about, I think. So the question is, can we...
My response is the same as it was yesterday.
Which is what?
That they're analogs of scores, at least for the particular class of hypersurface that I mentioned yesterday. Right? They're a game state evaluation system, but only in the foliation choice that maintains maximal stability between neighboring hypersurfaces.
Well, so your basic claim is that if this is, let's say this is score -1, this is score +1, you're saying that if we can label each of these things by some kind of score, that represents its position in branch Hill space, basically.
Well, what I'm saying is more precise than that, yes. But
say it more precisely then.
Well, so if you pick the particular foliation choice that maintains maximal stability between neighboring hypersurfaces in your coordinatization, right?
Yeah, I'm not sure that seems non-trivial to pick, and it's not even clear what it means to say maximal stability, because there's lots of different values that could potentially change.
Why? I can just, if I have a coordinatization, I can compute the norm of...
Fine. I mean, you can choose a norm, L2, whatever, L1, whatever it is. But I mean, there's stuff to choose. It's not self-evident. It's not trivial to say what it means that the thing has minimum change. But yes, you can certainly define some norm for which there is minimum change.
Well, if you pick a coordinate system, there's a canonical choice of norm, and then you can...
If you pick a coordinate system, you're saying, if I have a bunch of points, so let's say I've assigned a value to each of these things, right? And I mean, based on Ed's threat model, can you assign values to these things here? Or is it not very interesting to do that? Because
yes, you could, because you basically subtract one, and each one of these has one in a row, basically, so you'll win on the next turn.
Okay, so can we compute for each of these what the threat? I mean, what the kind of? I mean, there's a pair of two things: an orange value and a purple value. Is that right?
Right, and in each of those, the next player will win.
I understand that, but I mean, if I were to take those particular, if I were to just take, look, if I were to take these things here, that there's these configurations, right? There are the possible configurations. Can you tell me what your pairs are for each of those configurations?
Yes, but it's sort of meaningless for 2x2, more interesting for 3x3.
Well, what does it give for 2x2? Does it give different numbers for different ones?
It's just basically saying that there's one cell on the board, because the next cell of the same color is going to win the game.
Wait a minute. Are you saying that the numbers are equal for all of these cases?
Yes, pretty much, yes.
Just a minute. Go ahead. What were you saying? That sorry, what were you saying? That for each of these, there's just a single number, or is there two numbers?
Pretty much the same number.
Okay, so we have to go. You're saying we have to go to 3x3 board before it's at all interesting.
Right.
So
Because
if
there
we
you
went-
could have two cells of the same color that aren't on the same row or column. And that would be threat 0. And if there was two in the same row or column, that would be threat 1.
Okay, so in this case,
Oh, that's also unblocked. If a row or column is blocked off, if it has both colors, then it's not counted in threats anymore.
okay, hold on, Ed. In this picture, can you give coordinates? Can you give these threat coordinates?
Yes, they would all be threat 0 because none of them have 2 in an unblocked row. You need to go to the next step before you start having things of interest. Right, so that one at the very top, for example, is threat 0 since the purples aren't in the same row or column, whereas there's plenty that have 2 of the same color in the same row or column. And there's a few here where there is all the colors are on the same row and column, and therefore that row or column is blocked.
All right, so fine. So we can, for every one of these, we can say, for every one of these, we can assign a pair of values, right?
Right. Yeah, orange has threats, purple has threats.
Okay, so those pairs of values, I'm trying to understand, do they follow Jonathan's principle about coordinatizing the space?
I don't know.
Can we actually compute the values of these things? Is that possible?
Yeah.
What is the computation? Just give me, if you just have a piece of code that does the computation, I can fill it in this picture and use that as the state rendering function.
Sure, I'll write that.
Okay. But meanwhile, I mean, I'm still a little bit, I mean, maybe Jonathan fully understands this. I don't fully understand how okay, so the question is, like, if we wanted to work out a path integral, I mean, in what I mean, I'm trying to understand. Maybe Jonathan, if you're with us.
Yeah, what was the question?
Okay, so I'm trying to understand what the analog of a path integral is for this kind of system.
Sure.
Right? Where we start with some state, and we're effectively asking, what is the phase change to get to another state, right? So in other words, if we were fully coordinatized, that would be a meaningful thing to ask, right? Does that make sense?
Of course, but what's the question?
The question is whether we can have a simple example. What the analog in this game of asking the question, what is the phase change to go from one, each path involves a certain phase change. Well, actually, look, the obvious thing to also look at is what the causal graph is like for this thing. What is the causal graph for this game? That would be asking, given, how do we make a causal graph? And does the code work if we put in an event? What functions do we have to put in order to be able to make a causal graph here?
State event function, event decomposition function, event application function.
That's a lot of functions. Is it what's the cheapest way to be able to do this? I mean, in other words, what do we have to, okay, first question is, so an event here is we're adding a cell, we're adding we're just adding something at one place here, right? That's presumably our event. So let's see. The causal relationship is simply, we might be able to do some cheap way of doing this by turning this thing into a string, right, and turning it back again. And then we could just use the string code.
Right.
But so do you agree that this thing is, can we use the same event? I mean, how difficult is it to write? Okay, so the event decomposition function requires that we actually have a representation of the event, which includes the position at which the change was made and so on, right?
Well, yeah, yes. All three of the functions I mentioned require having that specification.
Is there an obvious such specification, or should we just try and hack it and make something where because if we were doing this just with strings, if we weren't trying to figure out whether we've won or lost, it will be fairly trivial. This is a fairly trivial system.
Right.
If I'm not mistaken. And basically the only thing that's non-trivial is the state rendering function. So if I just say string analog, this would then be, can we do it can we do something where the function depends on the turn? Is that possible?
Well, we can do it in the same way we did yesterday or the day before with, where the evolution function depends on the step number.
Right. I have to remember how that worked. Is that an argument to the?
That's just an include step number goes to true and then use the first.
Okay, so then here, what we'd be doing is we'd just be saying, somewhere we'd be saying if even q so we have to give a state evolution function, is that correct? We can't, or do we, or can we do it with just a function that looks up the first and last? Does it work with just a function, or do we have to give us an explicit state evolution function?
I don't. Does what work with just a function?
To do a thing that depends on step number. So is there a way to do a thing that involves that is just? Do you understand what I'm saying? That includes the step number. Do we have to break it apart like this? Or can we just say, take this thing and what is given to it? If we didn't have a state evolution function and we just had an initial, oh, I see, we can't have an initial function. We have to have, right, so the rule then, I see. So here, what we basically say is the state evolution function, we can't have something which just has a string replacement with an if in it. Presumably we can't, right?
Correct. I mean, obviously we can as a state evolution function. If you mean, can we do that as a first argument for a multi-way system with no additional wrapping, then obviously no. Okay. I don't know why that would work.
Okay, so then if we say string replace list of last of hash, comma, 0 goes to toString of mod of first of hash, comma, 2, 1. Okay, let's see if this is totally wrong. Okay, not good. All right. Okay, any idea what I did wrong here? Okay, string replace list. So this is the initial. Are you looking at this by any chance, Jonathan?
Yeah.
Okay, do you see what I did wrong? Last of this. Why is it saying last of that? It says include step number. So why isn't the last here? Why isn't that getting? Okay, so I don't understand. This is not including the step number.
Yeah, but you've written a state evolution function that doesn't include step numbers, so I don't really understand what you're doing.
Okay, so why don't you tell me that? I'm sorry, I made a mistake. So could you just tell me what? Okay, so this should be first of hash plus 1.
And you didn't specify a state rendering function.
Why doesn't it just default to just be? Last of characters of nothing.
I think your last is in the wrong place.
Getting closer. What did I do wrong here?
At 30.
Oh, no. I know what the problem is. The problem is there's a 2 expression missing here. There we go.
I also
Okay.
sent the threat level code.
Now, is this the right? Why does this look different from the way it looked before? This is what it looked like before. Why is it looking different now? Let's see what it looked like with 2 steps. Oh, wait a minute. I'm very confused. Why is this different?
What do you mean? They're not up to the mod.
Oh, this is,
If you do mod first hash +1.
yes. Okay, first of all, that's the wrong code. Let me get rid of the echo. Okay, so now if I go to 4 steps, that's not the steps, that's the steps there. Okay, that doesn't look the same.
How so?
Well, I guess it's just a re-rendering of the graph. Yeah, I guess it is the same. Okay, good. All right, so then this here, we can presumably take and say, instead of states graph, what will it do if I have a default, what is the thing called? Evolution events graph? What is it called? What's the thing called that has events?
Yeah, evolution events graph, which won't work.
Unless we give it an event rendering function.
Well, unless you give it a state event function and event application function. And
How can we generate a causal graph here?
no. Again,
Wait a minute. We've got strings. Everything at the lowest level is just strings.
I know.
So why won't it work in that case?
Specified in this. You haven't specified an event function, an event application function, or an event decomposition function.
But they're just strings, so we have defaults for those, don't we?
Well, we do for a pure string substitution system, but you've set them all to be identity.
Okay, but so what is the default for a string substitution system? Because that's what we want to use. So, this would work. This would be a pure string substitution system if it wasn't for the fact that it varies with time step.
I know. I know what this is.
Right. So what I'm asking is, how do we do this? How do we set this to be correct for a string substitution system, given that seemed to be easier than going in and writing these explicitly for the actual data structure that we have?
Yeah, right. I agree. It's easier. So just you put in the state event function, the event application function, and the event decomposition function for the string case.
I know. So should I go look in the code to get those? Well, what's the best way to get those?
I mean, I can send them to you if you'd like.
Yes, that would be good.
Except that we still need to pick an event specification.
What do you mean an event specification? Why do we need that? I mean, the thing, we just have strings, so it's just going to use the event specification for a string.
Yes.
Which just says, I mean, it's going to be some trivial thing that says the string has, we could just draw it, rather than using this fancy thing here, we can just draw it as one string on top of another.
I know, but what the state event function does is it takes in a specification of a state and it gives you a list of events. Right?
Okay, so the reason we go wrong here is because we're alternating time steps, correct?
Well, it's because we have non-trivial code on the right-hand side of the string substitutions.
But it's only non-trivial. It would just be a string substitution were it not for the fact that it has to vary with the left-hand side.
Yes.
Okay, so whatever that code is, I mean, so okay, can you send me or should I just go pick it up from somewhere?
But it's not going to be of any use until we pick an event specification, right?
But the event specification could just be the string event specification of just.
What is the function that takes in a specification of a state and outputs the list of events? It's definitely not the same as it is with the strings case because there's non-trivial code on the right-hand side.
It is the same. It's just all it's doing is at each step, instead of it being the same, whatever the strings case does with the string, update rule, this is doing the same thing, except the string update rule is different for. I mean, we could equally well run this. If it wasn't for the fact that the whole point of events is that they connect different time steps. We could just run this one step at a time, and it will be exactly the same as for the strings case.
Yes.
Why don't you just show me the code? Because I think it's
Okay. This is obviously not going to work, but you can take it.
What is this function? What is this function? So this is
the state. This is the event function for strings. Or, I mean, actually, well, this plus that will convert it into event functions. But like I say, without picking an event specification, this is not going to work.
Okay, but I think the event specification should be exactly the same as it is for strings. I
keep saying that won't work because we have non-trivial code on the right. I agree it'll be very similar, but it won't be the same.
Okay, so this is, where does it get that rule from? Where does it choose? It's getting that rule. How is that being propagated down? Oh, I see. This thing, I see. So this, in fact, all it really needs is this because it has the rule. We're giving it the rule.
Right, exactly. And so, yes, because there's no non-trivial code on the right-hand side of the string substitution rules. In this case, we have non-trivial code on the right-hand side, so we need to pick a different event specification.
Right. Well, I mean, this thing here, let's call this x get whatever, would just say with rule equals blah, 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 and then it's that, I claim. And that rule is a string goes to string rule, I claim. Okay, and the string goes to string, I think, is just this. Where instead of that, it's step number. Do you think that's right?
Yep.
Okay, so x get, so this doesn't need rules in it. Doesn't need that, right?
Correct.
That was a rather unprofound function. Okay, so in fact, this is whatever. Okay, all right. So now in here, we would say what we would say here.
State event function goes to x get string state event function.
Okay, Is that all we have to do, or do we need an event decomposition function?
It depends what you're trying to do.
I'm trying to make causal graphs.
Well, then, yeah, obviously, as a state, we need an event decomposition function and an event application function.
Okay, can you send me the ones for strings?
Yep. But you should test that this works first.
How can I test that?
Getting all events list.
Say it again.
By getting all events list.
Remember, Jonathan, you wrote this code. I didn't write this code, so it's less clear to me what, okay, what's that null goes to? The heck is that? Okay, what did that do? So this is saying replacement. Is that the initial event? Null?
Yeah.
Is that what's going on?
Right.
So this is supported. I don't understand. Why did it do this? Because that would be the initial event. What do we need to put in here to support that initial event? Why did it get called with this? This is not even the same structure. Oh, string replacement event. No. Why did it get called like this? Wait a minute. This says state arrow string. What does the string replacement event do? That takes a string. Is that right?
Yep.
And what is it supposed to return? So if I take this thing here and I say one arrow string 0, 0, 0, 0. What? Oh, very stupid. Look. Look. Trivial mistake. Okay. That looks like that. So that looks reasonably convincing, right?
Mm-hmm.
So now why is it doing the wrong thing here?
Because we don't have an event application function.
Okay, all right. So what do we put in for the event application function?
So we can do this, I believe.
Can we do that literal thing, or do we have to change it?
I don't think we have to change anything. Okay, and then now, I think I did.
We need an event decomposition function, probably.
No. That's obviously not it. No. You need to extend your definition of the X string replacement event.
What is this thing? Yeah.
So it can deal with the list case. Honestly, you should get rid of the rules because that's deprecated.
Oh, we don't need to slash out rules here, right? We just say.
Yeah, you can get rid of that. You can get rid of the slash out rules and the interior catenate.
This catenate here.
I believe so.
Prompt Promising. Okay. Now what do we need to do? What else do we need to get something reasonable to come out for an event graph?
Oh, for an events graph, nothing. I mean, other than the rendering code.
Okay. So let's take a look at what this does then. For what do we want to ask for? Which one should we ask for here?
I thought you said an events graph.
Okay.
So it's an evolution events graph. Except there's no event rendering. So that won't work.
Okay.
Structure, it'll work.
If I do what?
If you were to ask for the structure, it should work.
Okay.
That's not a good sign.
No. Well, let's try to put in an event rendering function. What does the event rendering function? What arguments does it take?
Let's see.
Does it need an inset and things as well?
Yeah. I mean, it works just like a state. Yeah, it works just like a state rendering function.
What? Why did it say that? What did we change here? Include step number. Why would evolution events graph is giving some different
Well, it's showing us that there exist unevaluated getString event application functions in there, which is presumably why the evolution events graph structure didn't render correctly either.
Right.
So we should figure out why that's not working. And that may be my fault. Hang on, I may have not sent you enough.
Okay.
Try adding this. It's so difficult to debug code remotely, but
This is here.
right.
So this is another, oh, that's just another get string.
Yep.
Encouraging. Well done. Okay, so this is now okay. Let's try to okay. So let's put in a not totally stupid. How can we put in something here that is not totally stupid? Well, I don't mind just having a yellow blob here.
You could do what we do in the CA case and just show the input state and the output state side by side.
Yeah, but they're very obvious in this case because you just look at the two ends here.
Right.
Let's just do this. Graphics, yellow disk, image size, arrow 10. Oh, let's say orange. No, let's say darker yellow. Ugly. Close enough. Okay. So now we could also do this as a layered plot. So let's do this as a layered which will make it a little bit more obvious what's happening here. Okay, that is our standard no wins thing. Okay. Okay, so now let's say what is it? Causal, what is it called? Events, gosh, I forget these every time. A thing with causal edges shown.
Well, before we do that, we should probably add the event decomposition function.
Okay, what does that need to be?
Okay, I'm going to send you some stuff. This is going to be a little bit long, but hopefully not too long. That's the first bit. You want me to email this to you?
Probably is easier. I mean, if there's more than this.
Yeah. There are 3 parts. Let me email it to you.
Yeah. And then I mean, the next question, of course, is what in this situation, what does the causal graph represent in one of these games? And I should work out Ed's threat score on our.
There you go.
Okay. How many different definitions are there here? 1.
There are three separate functions, but one of them has 2 different definitions.
Okay. All right. Now, what do you think I put in here?
You put into event decomposition function. You put get string event decomposition function.
Okay. Anything else?
No. Well, yeah. Let's see what that does. And then you want to say evolution causal graph as your property. And that happens.
Okay.
Try evolution causal graph structure just so we can make sure it's not a rendering issue.
Okay, so let's take a look at what it actually does. Why does this have a Docker is not a graphics primitive? What the hell's that about? Well, I mean, not that this is bizarre if this has anything to do with anything. No. Okay, so let's try and debug what happened here. Okay, what does getString event application function getString event decomposition function? Should we pick up and look what the event looked like?
I highly doubt that's the problem.
Okay.
I mean, you can, but
Well, what do you think? Well, I mean, okay, so what we know, is there something else that's getting called in the middle of this? These are called with one argument. Wait a minute. Does it care about the fact that there's a step number first, or does it unravel that?
well, no, that's what I'm assuming it is. That just check something.
That's what the get string event application function is being fed, which I don't think is right, because I think it has to be the last of that, right?
No.
Well, it doesn't look get string event application function
Has an integer as the first element.
Okay, all right, okay.
I really don't think that's the problem. I think what the problem is that we only have, so I think the causal graph rendering code uses a combination of things with step numbers and without step numbers in order to assess causal relationships. And we've only specified the event functions and so on for the case with step numbers.
Okay, so what do we need to specify?
So we need to, I think it means we just need to add some additional cases for the, replacement event and things.
For what do you mean by replacement event? What was that?
The function x get string replacement event.
Okay, so you think we need to add the case without integer step number here?
Yes, probably. And what else could it be? I think that's probably it. Okay, so what we need.
Could we, to check that, what we could do here is does that confirm or deny your claim? Doesn't look very confirming of your claim, because those seem like they're all in the same format.
The input states are yes. Can we see what the event decomposition function is being passed?
Yeah. Don't you like this @ star? I just realized one could do that.
It's pretty good, yeah. I hadn't known that was, this would have made debugging a lot easier.
Yeah, I just figured this out. Now, is that what you expect? String event decomposition function. Is that what you expect it to be given?
Well, yeah, you expect it to be passed in events.
Yeah, which is thing goes to thing, prefix, whatever it is. Thing
Right.
goes to thing, left-hand side, prefix, suffix.
Mhm.
Okay, that looks right. Okay, so what else could be getting past something funky?
I don't know. Well, can we not try it on a smaller thing so we can actually analyze what the graph is?
Yes. One step.
Well, the vertex list only seems to contain states, which is a little concerning.
This was an evolution causal graph. That's right.
What's right?
That should only contain states. It's an evolution causal graph. It's going to have extra causal connections, but not extra states.
But it should have events in the vertex list.
Wait a minute. Doesn't an evolution causal graph just contain? Oh no, it has to. That's right. It has to join events to events.
Right. I don't understand. Can we look at the causal graph? Ah, interesting. Okay, run it for a few more steps.
So it's not connecting. So let's see what this is. Let's make a vertex list of this.
Oh, wait, hang on. Yeah, sorry. Yeah, I'm being an idiot. Yes, of course. This is a waste of time.
What?
This whole exercise.
Why?
Because once you've placed once you've placed something in an element of the grid, you can't then place something in the same element of the grid. So there will be no causal connections. Yeah, sorry, that's really obvious. I should have seen that. There's no overwrite, right?
That's true.
Yeah, that's what's going on.
There are variants with their overrides.
No, but let me understand what that means. That means the lack of any causal connections means what? In terms of thinking about this, what the heck does that mean in terms of our quantum interpretation of things? Well, I'm a little bit confused here, actually, because the fact that you've written in a particular cell implies you can't write in that cell subsequently.
Right. So
I don't understand why there are no causal connections, actually.
Well, because our definition of a causal connection is one in which the input elements have a non-trivial overlap with the output elements of a previous event.
Are we just not choosing to write in those positions?
Right. So what you're requesting is some kind of causal anti-connection, right? Where you're saying, which we discussed. We discussed this in the context of deadlock, right? What you want is the dual to the causal network, which says that once this event has happened, this other event can't happen. You remember?
Yes, I remember that. Right. What were we calling those? We were calling them...
I think I actually wrote some code for doing this, but yeah, I can't remember what we called them. Oh, they were like causal impossibility graphs or something.
Right. Yeah, we did have code to do this.
Right. I'll see if I can dig that up.
Okay. Because no writing in a cell can ever affect.
Yeah, so that actually, yeah, I'm annoyed at myself I didn't see that earlier. Yeah, because basically what that's saying is all events are space-like separated. They can't be branch-like separated because you can't have overrides. Right. Which is why
it's very weird that okay, so in this picture,
which is why you have a terminating rewrite system, right? Because you have a fixed sized universe, you have a finite speed of light, and all of your separations are space-like. So you have to eventually terminate.
right. Well, i.e., there are only a finite number of places to have something happen. And once it's happened there, you're done. Okay, so Ed, these are your threat scores, and so this claims, this is showing at different positions here, 0, 1, etc., etc., etc.
Mm-hmm. Yes.
How do we plot this in an interesting way? So I guess each point, let's see, 0, 0 could be white. What do we have here? Let's just see what we have.
Might do a 0, 0 goes to nothing and anything else is shown. And that way it'll be a clearer graph.
But they're always just plus 1 or minus 1. They're always, in this particular case, they're always 1, minus 1. So this one here, we could just say, slash dot. Okay, so that shows where each side has an advantage, so to speak.
Right.
And then we could get more intense advantage or less intense advantage. That's kind of interesting, actually. Does that surprise you in any way?
No, that's pretty much what I expected.
Okay. So this is showing, actually, this is kind of interesting, Jonathan. This is like phase in branch hill space. This is kind of supporting your, part of the story of if you map it onto one dimension, it's complicated. Okay. Okay, a couple of brief things, and then we should probably wrap up. But I thought this was fairly interesting. I mean, maybe I have the feeling that Jonathan thought it was tiresomely trivial.
Well, I must confess, I was kind of hoping we'd get to the case of this, which I think is going to get really interesting, because I think there's stuff that we don't yet have intuition for in regular multiway systems, is something like the backgammon case, where in effect you have two measurement events that occur sequentially, right? And that's not something we've yet investigated directly.
What do you mean by two measurement events?
So in backgammon, you have the two phases. You have an initial phase where your objective is to try to get all of your pieces onto your home board. And then you have a second phase, which is where you then want to do the bearing off. You want to get rid of pieces from the home board.
See, you guys have such an advantage over me. I don't play these. For like 40 years, I basically have not played games at all. So I'm merely a studier of their kind of
It might be worthwhile to mention an unsolved simple game, and that's 6 in a row, where the first player places 1 stone, and the second player and thereon you place 2 stones. First to get 6 in a row wins. It's an unsolved game.
sorry, this is on a different size board, but this is like tic-tac-toe. Is that right?
Right, it's basically an infinite board.
Okay, I wanted to ask about infinite games. Right, you're saying that's a simpler version of a backgammon-like situation. Is that right? By the way, emergency temporal shift is asking, is that star new? No, not terribly new. It's about 4 years, 5 years old, I think.
That's an excellent Doctor Who reference, by the way.
The Danielle is posting on this about I was put off backgammon because, well, I played it like once ever. I did play chess at one point. I played it until I was like 7 years old until anyway, for a while I used to win against all kids, and then I stopped winning against all kids, and then I stopped playing it. Which is probably a bad story, but okay. So hold on a second. So what you're saying is, because I was going to ask about infinite games, because that's another thing I really was interested in, because yeah, but by the way, okay, next question. I was going to ask about causal invariance in these situations and what it means in this game, right? There is causal invariance here, is there not? Fine causal invariance. Isn't that correct? I think so. I can just say causal invariant here. Yes, as it should be. What does that mean? Why is it saying it's not causal invariant? After 3 steps, it has not reconverged. Is that right? What does it mean for the game that it takes n steps to be causal invariant?
Well, that you don't know until a certain number of flies have occurred, who's going to win. If I make a decision, I don't know several steps later whether that was a good decision or a bad decision.
Okay. How does that relate to the curvature of the space, and how does that relate to like non-commuting? I think one thing I was going to look at, I did start to look at, okay, let's see, what dimensional is the space? Do we know? Could probably figure that out very easily from something like this. Well, let's do it from this one here, first of all.
Well, it'd be 3, right? You've got the 2 dimensions for placement and time as the 3rd.
I don't think you can say that. I mean, that's the question of, okay, you're saying in this graph, if I say, oh, great. I need to remember how to compute these. Anybody remember this? This requires log differences, as I recall. Does mean around work on that? Is that right? No. Oh, for God's freaking sake. Oh gosh, how does this work? Anybody remember how to do this?
Not off the top of my head.
Hold on, I'll find it. What? What? Oh, I see. There are some of these that are very, very short. Well, let's see what happens if I just do this. Actually, Ed, you were surprisingly correct. You were surprisingly correct. How did you know? Well, how did you know it was going to do that? What was your argument for why the dimensions of this thing should be about?
I don't recall what I said now.
You had an argument for why the dimensions of the thing would be.
Well, because you have two spatial dimensions of the board and one time dimension, and because
All right.
one at every, one point is being filled at every step, you would therefore expect to be three-dimensional.
Okay, so what do you think will be the case in the winds case?
Oh, it'll be the same.
And you're correct. So, okay, so this, do you reckon that this is a curved space? Because
Well, I would say it's finite, so I don't think it would really count as a space.
well, okay, but imagine a bigger one. Right, so imagine a bigger one. We can compute, presumably, the curvature of it, right? Because what would cause it to be just a grid-like thing? If this was one-dimensional, it will be a grid-like thing, wouldn't it?
Mm-hmm.
In other words, if I just made this the 1D case. Okay, so if I say here.
Right, so let's define this game. We've got 0 to infinity, and the first one to pick 3 numbers in a row wins.
Okay, but let's look at this guy here, because this is the case of why is that? taking so long when the other one took? Oh, wow. I don't understand this. This is the case. This is a case for a one-dimensional game, right? So if I were to, is this going to work correctly? Or do I need to say, here, let's try this case here. Maybe it is working correctly. Okay, so let's say 5 or something, 4 there. Okay, so now let's say, why is this not working correctly? Oh, states graph. Okay, well, apart from the fact that it needs to be transposed there. Okay, so there's the trivial case here, right? Do you agree this is the right thing here?
Yes, looks like it.
Okay. What is this graph? Is this graph something totally obvious?
Doesn't seem obvious. No.
It's some kind of subsets graph of some kind or something. So you reckon, I mean, we should be able to compute whether this graph, what the curvature of this graph is. So if I now go to, let's say, I don't know, 8 of these or something, 8 steps. Okay. That looks surprisingly similar to the case in, okay, so now you can define a win, you're saying. You can define a win, for example, when there are 3 in a row. Is that right?
Mm-hmm.
How will that be similar to or not the same as? But I mean, okay, but just, sorry, in terms of our dimension computation, okay? This one here. Okay, that also says 3 dimensions. Explain. Let's try doing a much bigger case. Let's see what it does for a much bigger case. Let's say 12, 12. Forget all these things. Oh, God. Okay, let's just try a smaller case here. Let's try 5, 4, 4, 4. Okay, that was our previous thing. So let's try 5, 5. These are always giving the layered graphs. 6, 6. Okay, so this is some object. This is some nice 3D object. I wonder what that is. It probably has some very simple group theoretic properties. It's probably not that different from that Turing machine thing that I was doing.
Mm-hmm.
Okay, so now we can ask what's the dimension of this object, right? Okay. So let's say we go to like 12 here. It's a little more dangerously 13. Okay, explain that picture.
I don't know. That's for 1 by 13?
Yeah. I have one possible idea here, that if we make this be an undirected graph, that it'll be more useful.
See if a 7 does 4 dimensions.
Hold on. Makes no difference. What, 7?
Yeah,
Okay.
because 13 seems to have done 5.
Oh, I see. It's just the number of independent degrees of freedom you're saying.
Right. The 7 is that.
Oh, it's about 3 point something.
Mm-hmm.
Okay. Look, okay. We need to wrap up, but okay. So there's several points. First of all, there's a possibility of infinite boards. And in which case we will have, I think, Ed, you were going to explain to me how things like nimbers work, because I'd worked out here for the case of nim, right? So by the way, Jonathan, this might be of interest to you. So for these games like sliding block games, right, the structures are more elaborate, right? They often have these holes in them. The multiway graphs aren't sort of compact structures. They're things with lots of holes.
Yeah, usually there's a group theory involved with them.
Yeah, well, so these this is various kinds of sliding block things. Is this obvious to you, Ed?
Mm-hmm.
Why?
It's a well-studied field.
Okay, so what are things like this?
Also, it's the moving day puzzle I sent you earlier. And it's so well studied with plain blocks that they go to dominoes and trominoes to make it more complicated, and that's where it starts getting unsolved.
But right, but I understand. But what they're trying to do is single paths, which is not what we're doing here. They're interested in single paths, and I understand that that's one set of
Oh, you can get universal computers with those.
With what?
With dominoes and trominoes, it's possible to set up logic circuits.
Yes, I've seen that. That's in what is the case where that's known? Yeah, I mean it's in these rush hour like puzzles, right?
Right. Mm-hmm.
But how would that show up in, I mean, so these graphs, what would be the analog of these graphs for a logic circuit? In other words, this graph represents the how you go from state to state. How do you read out a logic function from these?
Well, that's more complicated. I'm not sure, because most of the big study is done for smaller cases where you can completely map out everything, and the question is how complicated can you make it? For those logic circuits ones, those rely on much larger cases, And basically, they're just trying to show that a logic circuit exists. They're not trying to show all states. But with their argument is with a sufficiently large slotting block puzzle, chaos starts at some point because you've got all possible computer circuits.
Nonsense. Nonsense. Not a correct conclusion. I mean, that's different. Those are utterly different statements, right? I mean, this you can have all possible circuits while still having all kinds of structure. The fact that it's not even obvious to me what it means to have. So you're saying with some initial condition, by encoding the initial condition, and again, it's got to be an infinite board if it's actually going to be a Turing machine. By encoding the initial condition, right, you can get, yeah, I understand. But it's not going to be the case. This kind of structure here will still exist, even independent of that.
Yes, yes.
And it'd be nice to know what these structures are. Maybe these have been studied, maybe they haven't. I don't know.
Yes, Knuth has studied some of these.
In that book that you just pointed me to, which I need to look up.
Right.
I should remember to send Don the whatever I write about these things. I didn't know he paid attention to these.
Well, when they're connected with anything classic, I think pre-1940s, he's quite interested in studies that haven't been completely analyzed yet. If it's the first case of a classic puzzle, basically.
Right. Well, so the other one I was looking at, so I looked at these. Okay, so I was also looking at NIM, where and my understanding is that in terms of valuation stuff, there is some systematic way to value NIM. Is that correct?
Yeah, bit XOR.
But my question then is, if I look at, okay, here's NIM, and here's a bunch of NIM moves, right? What do you mean there's a systematic valuation?
Oh, usually they go to bit XOR for solving the game.
No, I understand. I'm not interested in solving that. Solving the game is you're trying to find a path, right?
Right.
So this is a typical game. 333 goes down to 000, right? So a particular game is a path through here, right? And there's probably an optimal path, and it might be given by bit XOR. But my question is, this whole Nimbus technology, isn't that what I'm interested in? Is the relative valuation of different configurations that one's in at intermediate stages here.
I don't think that's really numbers anymore. Basically, that's going through a coordinate system where you've got leapers of different sorts.
Got what?
Leapers in a chess. Knight is a leaper. So for this, you can consider this three-dimensional leapers of various sizes being valid, and how the coordinate system is connected.
But so wait a minute. So you're saying that you're saying the closeness of two, the effective closeness in a picture like this, right? So if I'm like, I make so here I've got my random NIM moves. Okay, this is not foliated like game moves, I say. I wonder how you would foliate it like game moves. I guess, can I say evolution graph, or does that not work unless I specify lots of other stuff here? I am about to find out. That doesn't work. Okay, so I mean, my question here is, Are you saying there's some way to value different configurations here?
Right. Basically, I would, what are all the possible changes in state? And that would be your set of how coordinates are connected. So for example, if you've got a 3x3x3 grid, you can move orthogonally one space. That's one boring example, but you're also adding extra possible moves you could make from.
Wait, this is NIM.
But basically, you've got 3 piles and you're removing stones. So you can basically treat all possible moves as coordinates in a 3x3x3 grid. And it's how these points are connected.
Someone is commenting on our live stream that games like Simon Says or musical chairs may have behavior that mimics quantum mechanics. What are those games?
Musical chairs, when the music stops, everybody tries to sit down.
That part I know that, yeah, but right. But I don't understand what's the mathematical version of that?
You'd have random points and some goal places.
So as soon as there's randomness, it's not interesting. What does Simon Says?
I tell you to do something, you do it. And then I try to trick you by not saying Simon Says at the start.
I see, okay, fine. All right. Okay, but back to this. So do you understand this theory? What is the theory of these number things? And what is the theory of how they get to be transfinite numbers and so on? What is the relationship? All the stuff about games and ordinals and the transfinite versions of these, does that happen in NIM, or does that require other games?
It requires other games, I'm pretty sure. Numbers are useful for analyzing Hackenbush, but the various hotness and stuff like that of games requires more stuff.
How do you play Hackenbush?
It's basically a graph of 2 colors, and each turn a person can cut edges of their colors, and the last to cut an edge wins. There's a rooted part of the graph, and basically every part of the graph that's disconnected is completely removed from the game.
Oh boy, that sounds really complicated. It sounds like some minimalized version of Go of some kind, where it's like, things are alive, they're dead, they're cut off, they're not cut off.
Right. But basically that leads to surreal numbers. Most games can be represented in Hackenbush.
Really?
Mm-hmm.
So how?
Well, most finite 2-player games.
But so wait a minute. So you're saying that it is something where we can remove. So how do we have examples of this from demonstrations or something?
No, Hackenbush is a little bit too complicated for that. I could think about how to do that.
No, but what basically is okay. So you're saying you.
So one good case to think of is.
Why do I suspect that this game is basically a version of Goodstein numbers, and it was invented by Conway because it's like Goodstein numbers, but that he forgot to tell everybody that.
That's possible.
You probably don't know how Goodstein numbers are invented as a way to make to explore the boundaries of recursive functions. But so okay, so what you're saying is, so in this game you have some rooted tree or graph.
Rooted tree, graph, string.
What's string? How do you do it with strings?
Well, I'm thinking more of a tree graph that is basically infinitely long and doesn't have any branches. That's say red-green alternating to infinity.
Okay, so like we're talking, table mod n to 1, n goes up to 50 or something.
Right. Mm-hmm.
Okay, now what?
So that is an example of one Hackenbush position that complicates things, because if somebody wants to waste a move, basically lose tempo, they can just basically chop an arbitrary point in that, but eventually the chopping runs out, because as soon as anybody touches it, it becomes finite.
Player one is able to chop their edges out, or what? How does this work?
Yeah, basically either player can chop their number any place, and then everything after that gets wiped out.
So if I make a random graph, can I make a random graph and then put edge labels, and then I randomly put edges on the random graph?
Yes, and then you'd need to root some of the, like for example, that top corner could be the rooted part. And this would be a very complicated Hackenbush position. But whatever color that first edge is, that color would have the advantage, because they could just cut that edge at the start.
So wait a minute. So half the edges, so I could randomly assign half the edges to red and green or something?
Yes.
Okay. So let's say I say random graph, and this, and I could say edge style, arrow, let's say, well, let's just see what happens if I do this. I wonder if this will work. I bet this won't work, but we'll try it. Nope. Okay. All right. I might need, do I need connected? Well, there, I've got a connected one. Okay. So,
no, it doesn't need to be connected. This needs to have roots so that removing disconnected parts makes sense.
okay, hold on. So we're saying hash arrow this / edge list of RG. Okay. All right. So now I've got a red-green graph. I mean, a red-blue graph.
Mm-hmm.
Okay. So now you say, what I do is I say edge delete of some random edge. Is that right?
Right.
And then so I might say edge delete in that graph. I don't know, edge. I got to find an edge. I'll say random choice edge list of that.
All right, let's do a Hackenbush variant. We have that graph there. Blue goes first, red and blue alternate, and whoever removes the last edge wins. And anytime there's a larger part and a smaller part, the smaller part gets erased.
That is a mess. Why is that a generalized version of other games?
Because usually there's a pairing with a Hackenbush graph connection and a finite two-player game.
So for example, tic-tac-toe, what's the Hackenbush story of tic-tac-toe?
That one is not the equivalent to Hackenbush. It's one of the ones that's not.
Okay.
Because with tic-tac-toe, ties are possible, and that's not possible with Hackenbush.
Okay, so what about a sliding block thing? That's a one-player game.
No, because it's only one player. However, there is the game Domineering, where people alternate playing horizontal and vertical dominoes, and the last to play wins. That one is equivalent.
Okay. What's another game that's equivalent?
Oh, well, there's a lot. That's like all of Winning Ways is devoted to these Hackenbush equivalents. Amazons, for example, is one. That's a game where you've got 8 queens, and each turn you move your piece and then remove a cell that is in a queen's move away. and the last to move wins.
Let's see, there seems to be a thing called hack and strings. What's hack and strings, I wonder?
Probably a variant. I haven't looked at it.
But it seems to be a simpler thing. What's this? Hack and strings. I don't understand. Okay. Surreal numbers, which I think I at one point vaguely understood. Okay, so this is, I see. So what does this mean? This means that in addition to the that's actually a useful picture. That's a quite useful picture. I think I had some comment about surreal numbers in the NKS book, where I think I had, which is always a sign that for one brief moment I understood these. As generalizing numbers. Okay, that's not very useful. And I think this is one of these references where it doesn't actually appear on the page. Oh no, this representation is related to surreal numbers. Can consider any base 2-digit sequence as consisting of successive runs of zeros and ones. So in other words, you're representing it as a run length encoding of some kind.
Mm-hmm.
Is that right?
That's right. Yep.
So why is that relevant to games? Is that
because usually you're trying to limit what your opponent can do so that you have the final winning move.
so?
So basically any move that obviously gives you an advantage is the move you usually want to take.
Why does that have anything to do with run lengths?
Because it's usually a finite game, just being able to eliminate one of your opponent's moves that can usually be enough for you to win the game.
By the way, Gecko on our live stream suggests Toads and Frogs as an interesting game.
Mm-hmm.
How does Toads and Frogs work?
Basically, you can move one or you can jump if the space beyond an opponent's frog is empty.
So it's a one-dimensional game.
Uh-huh.
And determining the value of an arbitrary Toads and Frogs position is NP hard. Great. But so the question then is, I mean, that's interesting. I like these things that are one-dimensional because you can, I see. Left player, right player can move too. So what is the set of, what is the transformation rule here?
Transformation rule, what do you mean?
Well, I mean, what's the multiway system that you would get from this?
I'm not sure. It'd be similar to sliding block, but with it's basically a two-player sliding block.
So it's a one-dimensional sliding block
Mhm.
with jumping, with some kind of jumping rule.
Correct.
But by the way, I mean, these surreal number things, they come up in cases where there is an infinite game.
Yes.
Right?
Mm-hmm.
And we need to wrap up in a moment here. Ed, I need to pick your brain some more on this. This is my, I have avoided, there's so many things now, like between higher category theory and theory of games. These are both subjects that I have long avoided, so to speak.
Mm-hmm.
And that, who knows, may even be related. But somehow this, I mean, I'm kind of interested in all right. We should.
One of the more useful ones is turning turtles. Have you heard of that one?
No.
Basically, you have, say, 8 or 24 turtles in a row, and you can turn over any 8 of them. But once a turtle on one end is turned over, it can't be touched anymore. And if you play this game, you basically find out that the optimal moves gives the binary Golay code.
Okay, I'm not super surprised that there are things like this. I mean, yeah, I'm not at all surprised that it'll be right. It's a error correcting code, aka a sphere packing, aka something which has maximal distance between different. I mean, those Golay codes are also Hadamard matrices, aren't they?
Yes.
All right.
And that led this one branch of game theory into coding theory, and that's where the money got made.
You're saying turning turtles gives
it, well, at least it led to the greedy algorithm.
I see. All right, but this is okay. It's a 1D. The Toads and Frogs is a 1D sliding block 2-player game. We should wrap up, but look, the big picture here is that these game trees are bizarrely analogous to. I mean, it is very bizarre that it does appear to be the case that the winning of games is analogous to measurement in quantum mechanics. And I mean, not something I would have immediately assumed. And I'm still grappling with, how does one compute? Is there a way of computing essentially? I mean, the question is the path integral, so to speak, is that correspond to some strategy for playing games? That is, if you were to look at, if you are asking the question, or can you, is there some way of thinking about, change of phase is equivalent to change of position on the board, and then you're looking at path weights as a function of phase and things. Anyway, I just okay. Never mind. I'm still I feel like there is some. And then
oh yeah, I think there definitely could be a correction or correlation. That's one reason I like the turning turtles example, because basically you do this simple game and it generates what turns out to be the basis for the Leech lattice.
Right. Right. Well, but that, yeah, I mean, you're saying that this turning turtles thing could have a multiway graph, and that the optimal path in that multi-way graph corresponds to, I mean, so what is the multi-way graph for turning turtles?
I'm not sure.
Right, but then what you're explaining is that the Gallet code is the optimal solution, right?
Yes, for the 24 case, yes.
Right, but so that means that what the optimal solution is a path, is a geodesic path, basically, through this multi-way graph.
Yes.
And so what you're explaining is that somehow there's a, there's a connection between, which is quite an interesting thing, that there's a connection between some multi-way graph and this thing that is connected to all kinds of crazy group theory and so on.
Correct.
Yeah, well, that is interesting, isn't it? Very interesting. All right, we should wrap up here. This has been a long session, but although I'd be happy to keep going, but I know that we have practical constraints. Maybe I can reach out to you some further, maybe even Ed. I think this is your bailiwick, I think.
Yes.
And the fact that every game that comes up, you know how it works, is a sign of that.
But it might be faster if you just grab winning ways and page through it really fast.
I did that yesterday. I did that. I have done that piece of homework. I don't physically have it right here. And unfortunately, my copy of Winning Ways is starting to self-destruct. Its glue was obviously in.
Is it the 2-book set or 4-book set?
2 books.
Oh, okay. Yeah, those are rare now.
I'm sure I got it when it came out, and it's and I can tell you that it is the publisher did not provide. I don't think it's acid-free glue, but it's we had this problem with some early versions of the Mathematica book actually back in 1988, that the glue failed. All right, and Nick is suggesting this is the beginning of a game repository. We probably should have one of those, shouldn't we? Or at least we should have these things in. We should have WFR functions that yeah, okay. We should wrap up. All right. Thank you all very much. And thank you to folks on the live stream. All right. See you all soon. Okay. Bye-bye.